So now I'm going to present you Yufeng that is making a talk called TensorFlow Wide and Deep, Advancing Classifications the easy way. Please give a warm applause.
Thank you very much. My name is Yufeng, and I am a developer advocate at Google, working on machine learning, TensorFlow, that sort of thing. And so I want to start off with just a general, I want to take a poll of the audience. Can you raise your hands if you use machine learning in some way in your work or in your personal time, in the evenings for your personal projects, things like that? So lots of people, not everyone, but I'd say that was probably 2/3, maybe 3/4 of people. So that's really great to see. And as many of you know, of course, machine learning seems to be eating software, which is eating the world. So it's taking over. No, machine learning is really cool, and there's lots of ways to utilize it, of course. So today I'm just going to focus on one specific piece, and that's classification, so supervised learning, and classifying, generally speaking, here we're going to be targeting structured data. So not audio files or pictures or videos or people running around. It's CSV files, basically, or database tables. So I figured that would be kind of appropriate for this audience. You know, we had a number of workshops yesterday kind of talking about working with tables, compression, formats, all that stuff. So once you finish organizing your data and you're ready to do stuff with it, this is where we kind of pick up. So for the portion of the audience who did not raise their hands earlier, this is my one-slide overview of all of machine learning. Okay, maybe it's just a little bit of machine learning. So my definition of machine learning in the fewest number of words possible is using many examples to answer questions. 6 words. It took a while, but I eventually got it down to just 6 words. And if we take these 6 words and we now split them into 2 halves, 2 sides, we arrive at the primary 2 components of machine learning, the training and the prediction. And both sides are equally important because we want to be able to answer questions. And a lot of times we are lost in the training side and forget that the real purpose of building these models, of tuning them, of gathering the data, cleaning the data, maybe even compressing the data, is to actually use it for something, to answer these questions. And of course we can do this both locally and if we have a lot of data in the cloud, or maybe on many, many machines. Sometimes it's someone else's machines. And so today we're going to be using TensorFlow. This is Google's open source machine learning library. I think a few of you may have heard of it. And it was open source in November of 2015. So now it's been, what is it, almost a year and a half now. And TensorFlow is now at 1.1. Actually today, the 1.2 release candidate 0 just came out, if folks want to play with that. That just got dropped on GitHub today. And it's built to be not just fast and easy to use and all that, but it's also, at its core, built to be scalable. It's built on a distributed runtime. So TensorFlow, the name, comes from the word tensor, which is, I think, before I heard of TensorFlow, I had never heard the word tensor in my life. And so I was like, TensorFlow, oh, it sounds cool. I wonder what it means. It probably stands for something, right? So tensor is just another fancy word for matrix, which is really just a fancy word for array, right? If we twist the definitions a little. And then flow is referring to the tensors, these matrices, flowing on a graph, something like this. Nothing fancy, right? It's just some numbers going into an add operation and the result coming out the other side. Now the important byproduct of this structuring is that you have to execute it with what's called deferred execution. And that means you construct the graph first and then push numbers through it. So we'll see when we play with the code that there will be kind of 2 distinct phases where we do the construction and then we push numbers through it. And of course, TensorFlow supports many platforms beyond just the typical CPU and GPU. It also runs natively on Android, iOS, Raspberry Pi, and there's a special compiler called XLA, Linear Accelerated Linear Algebra, which allows you to actually write compilers for custom hardware, custom architectures, so you can put it into other embedded devices as well. And so as I was mentioning earlier, TensorFlow runs on a distributed execution engine at its core. Luckily, we don't have to work with it at its core because it's a lot of C++ code. And I know some of you probably really enjoy C++ code, but since it's PyData, we're going to be working with Python. So on top of C++, we have a Python front end. But even that is relatively low level. You are manipulating the graph manually by hand. And while, based on that picture I showed, manipulating the graph by hand seems like the natural approach, we can actually abstract to a higher level, and in fact, several higher levels. And first is layers. Layers runs on top of the built-in front end, and that helps you build basically layers of your network. But if you want to abstract even further, you can use what we call the estimator class, or use Keras. And you can use that, basically those libraries to help wrap the operation of even building the network by hand and take care of the entire training and evaluation workflow. And you can abstract it even further. And we have canned estimators, which basically takes care of the entire loop and supplies a number of built-in defaults that you can change. But a lot of reasonable defaults, best practices are built into that. And so we're going to play with that today because it's a demo, and the demo gods don't like complicated things. So this is this easy, kind of straightforward getting started. I call it kind of your first pass. Instead of putting your data into Excel and plotting a linear regression on your data, consider doing something like this, because we're getting to a point where running such a model is so straightforward that you can basically just do that as a first pass and see how it turns out, and then fine-tune it from there. So this is a simple example of using a canned estimator, and we'll get into the code. But the part I want you to pay attention to is that middle portion where it says DNN, Deep Neural Network Classifier. And so right here in the middle, the parameters are just passing what you need to. And you might say, well, what if I want to customize it more? Well, you can. You can customize it a ton. And there's lots of arguments. We won't get into all the details of these arguments, but this is just to show that you can do a lot before you're forced to build things by hand. So at this point, I wanted to step back from the code real quick and give you a little context for the model that we're going to be actually working with, the deep and wide model. So this is a little short story. So let's say you have a great new idea. You're going to build the next hot app. It's going to be great. And it's a magical food app. It's going to predict what your users want to eat based on what they say to the app and deliver it to them. It's totally original, right? So naturally, you launch and iterate. You say, okay, people say what they want, and we're just going to match what they say by text. It's going to be text matching, string matching. And so they say fried chicken, and you give them chicken fried rice. It's not really the same thing. People wanted fried chicken. They want something like chicken and waffles or chicken with like French fries, something like that, right? So that's okay. You say, I got a V2. V2 is going to use machine learning. You know machine learning, so you use machine learning and you train a linear model. And with the linear model, you can basically memorize what people's preferences are. And so now, you're doing pretty well. You're mapping, fried chicken to chicken and waffles, and you're saying, don't give them chicken fried rice if they say fried chicken. But if they say fried rice, you give them chicken fried rice. There's a problem, though. Users get bored because you've memorized what they want. So every time they say fried chicken, you give them chicken and waffles. Every single time. Right? So after the 4th or the 14th or the 40th time, people get a little bored, and so they want to see similar but different food. And so you say, that's okay, I know. We use deep learning. Yes. And so with deep learning, you can give generalized recommendations, and now your app is once again on the up and to the right growth curve. And you can give these generalized recommendations. And here I want to step back and talk about this concept of embeddings. With a deep network, what you get, why is it useful, is because you can embed your concepts, your food items into basically what actually turns out to be a lower dimensional space than it would otherwise. So in the linear representation, we basically have one giant array, one element per food, okay? And so maybe you have 1,000 food. Maybe you have 10,000 different foods. And so your array is that long. And essentially that's how many dimensions there are, 1,000 dimensions, 10,000 dimensions. But with an embedding space, what you end up doing is you get to arrange all of those food items into, let's say, just an 8-dimensional space, okay? And that allows you to cluster things that are close together, literally near each other. The example I use to describe how kind of picture this, because it's hard to picture an 8-dimensional space, right? So what you do is you take a piece of paper, 2 dimensions, and I say, okay, here's a blank piece of paper. I want you to draw a circle for every food I give you, and I want you to draw these circles near each other. And so, I start saying, watermelon, pineapple, strawberries, so you put all the fruits together, and then I start saying, chicken, fish, all these things, you put the meat together, and then I say, rice, pasta, noodles, and bread, and you put those together. And as I name more and more and more things, there are certain things that get a little tricky. Where do you put fruit pie? Well, it needs to be near the fruit, and it needs to be near the desserts. But I accidentally put the desserts here and the fruit here, and there's meat in the middle, and that doesn't really work. So you need a higher dimensional space. So I say, great, I give you a 3rd dimension. Here's a box. Now you can put things up, and you can arrange them so that things can be closer together where they need to be close, and things can be farther apart where they need to be farther apart. And so you can generalize this to more and more dimensions, allowing you to push and pull things where they need to be. So that's what an embedding space is representing. And by doing that, you can see what's close to any given location in that space. Great, so you've built a deep neural network. Your users are enjoying it, but there's still a problem. They are still picky. Why? Because when they ask for something specific, you are still giving them something similar. So when they say, I want a decaf iced latte with non-fat milk, and you give them a hot latte with whole milk, they don't like that. So you need to be able to understand when someone wants a specific request and when someone just gives a general request for some food. So you have to balance these two, right? And so basically the solution here is this paper that came out not too many years ago, like recent-ish, called Wide and Deep. And you combine these two. You could say, I'm going to take the wide or the linear regression and the deep network and put them into one big network. And this allows you to basically generalize most things. And then the wide side, it memorizes the exceptions. So wide and deep allows you to give memorization and generalization. And with these, by having it in this structure, you train it all together. Some things go one side, some things go the other, and it's all one big network. Now you might say, well, this looks like it could be complicated. If this drawing, which is just the cartoon version of the real thing, looks like this, then the real thing must be crazy, right? So that's why we don't want to manipulate the graph manually, because building this by hand, well, someone did that already. Right? This is great research, and so we should just be able to use this research, take advantage of this research, and work on top of it. Just leverage it, use it. And so that's the end of my story time, and we're going to now actually use it. So our data set is just as exciting as food. It's census data. Yes. And the task is to predict whether or not a given household has over $50,000 in annual income. And so this was from the 1994 census, so adjust your expectations accordingly. And there's about 32,000 training samples in here, and about 16,000 for evaluation. And so let's take a look at the columns. So first we have things you expect: age, education, where they worked, how much education. I already said education, but marital status. Things like their relationship, their gender, race, capital gains, how many hours they work per week, those sorts of things. Nothing crazy in here. And of course, last but not least, we have the income bracket, which is just categorical. Either you're above or below 50K. Now, the point I want to draw your attention to is that there are two kinds of columns here, primarily, categorical and continuous. Some columns are categorical in that they might just be two different values. All the values are just selected from 2 or 5 different values. And certain values are continuous. They span a whole range, right? Like things like age or capital gains. And so these two divisions, categorical and continuous, they map to our wide and deep. On the wide side, you have basically categorical things. You want to be able, you can basically sort of memorize those because they're just discrete values. Whereas on the deep side, it's continuous. So it's a continuous space. And so you want to be able to generalize among them. And another set of words that I'll use to describe this is sparse and dense. So sparse maps to wide, and dense maps to continuous. And so we'll see some of those terms pop up. And I'll try to mention all the different versions of the same word, but basically keep this in mind in terms of what really means the same thing. So let's go to the code. If you want, you can follow along on your laptops. This is the repo. I'll show it again at the end, but you certainly do not have to follow along. I'll show you everything on screen as well. So here we're going to be running in Jupyter Notebook, and let's see, the first question, as usual, is to ask, can you guys see this, or should I make it bigger? Any votes for bigger? Bigger. Any more votes for bigger? Any votes for smaller? Okay, nobody ever wants it smaller. So the first thing we're going to do is just import some stuff, nothing crazy here. TensorFlow gets imported usually as TF, so later we'll see TF in the code. It's mostly just so you don't have to type out the word TensorFlow every time in case you spell it wrong. And there's a verbosity setting here. Typically, you don't need to do this. The default will be worn. I'm going to change this to info, and this will give us more info, but it'll also give us a bunch of internal warnings and deprecation signals and things like that. So we'll scroll past those to the useful stuff when we get to it. And another useful thing I like to do is print the version of TensorFlow. Like I said, right now TensorFlow is 1.1. Until maybe 2 weeks ago, I had 1.0 installed. So whenever I run it, I like to see, what version am I running on? Am I in the right virtual environment? Things like that. And so we talked about there being categorical columns. So here I'm just storing some of the column names in different arrays. We'll take advantage of that shortly. So let me run this cell and let's move on. So the data is in a CSV. This part is, of course, optional in terms of TensorFlow, but it's kind of nice to play with your data a little bit, get a sense of what it's doing. And so here I just loaded into pandas and passed in the column names. And you can see here our data is pretty much what you'd expect. We have these are, of course, the describe only shows you the numerical columns. The data is distributed in some odd ways in some cases. You look at education number, right? It's a number. It's not an education category. So that's a number that goes, it looks like, from 1 to 16. And each one of those values maps to a different level of education. And you see here we have age. We are seeing ages ranging from as low as 17 years old up to 90 years old. And so with an average, median of 38, 37, mean of 38. So it seems to be reasonably representative. Most people are working about 40 hours a week, or 25 and 50, and even at 75, only 45 hours a week, so tight distribution there. And so another thing, and then here's an example of the actual data itself. So some of the columns are words, and some of the columns are numbers. So the other piece of pandas that when I found out about it, I thought it was pretty magical, is the computing the cross correlation between columns. This is probably, if what we're doing today is called the first pass, this is probably the 0th pass, right? Do the cross correlation, see if there's anything that directly maps to your answer in the first place. And you can see here there's not too much going on. Most of the values are on the small side of things. And so this is the kind of problem that you want to throw at machine learning. It's something where there's a little signal from every single column, but no one column that is dominating. Right? Even with that, you can use the little ones to improve your prediction, but here we almost don't have enough information to do a first prediction just using classical techniques. So with that out of the way, let's move on to more TensorFlow. So the first thing we want to do is, I have a function here that returns a function. And basically, this function is just getting the data into the graph. Plain and simple. It reads in the CSV. This is the boring part. So I'm not going to go into it too much. Basically, all you need to know is it's a function where, provided the file name, it will read that CSV and return a dictionary like this of the data. And TensorFlow, and we'll see how TensorFlow handles that. Oh, I should run these cells because that would be helpful. Okay. So now we get to the interesting part. We get to configure some columns. And this step is, I'd say, like a decent chunk of the meat of this approach. And what we have are called feature columns, right? So we have a library inside layers, which allows you to configure these columns based on whether they are categorical or continuous, sparse or dense. And the first thing we'll do is we'll deal with the sparse columns, the categorical columns. And we have two tools at our disposal. One is called sparse column with keys, and the other one is called sparse column with hash bucket. The keys with keys means that you are providing the values directly. You are stating these are the possible values for this column. So for example, in that particular census, the values for gender and race were just these few. And you can provide them rather than having TensorFlow detect them automatically, basically. And then here we have sparse column with hash bucket. And for this, it's in situations where you don't know the explicit, full range of possible unique values. So maybe you're collecting data from a form and you just decided to leave one of the questions free text entry. So people can type whatever they want, all sorts of garbage into there. And so after you clean it up, you're like, I still don't really know what all the possible things people put in, so you put a hash bucket size based on what you suspect the maximum number of unique values could be. And so I've just gone ahead and did that for these other columns. For situations where maybe you have like 100 columns and you don't want to type this out, using sparse column with hash bucket is a decent approach. You can just loop the whole thing and generate names for each column, C1, C2, C3. And so, see, I keep forgetting to run the cells. This has happened before, and then I get to the bottom and I say, okay, now we're going to run it, and then nothing works. So here we have continuous columns, right? So after we deal with the sparse columns, we have a couple of the continuous ones. They're much easier. You basically just map them to a real valued column. That's it. And what you'll notice here with both of these, when we did these, we never actually hooked it up to the data, right? All we did was we said, here's a real valued column. It's called age. That's all we said. We just said, here's a string. And so we're going to need to take care of that later, right? But for now, this is fine. And I need to run this cell too. Okay, so now that we have these kind of base columns, we can do a few transformations. This is kind of the interesting part. We've set up our base layer. We've mapped all the columns to names. Okay, of course we need to do that. But now what we can do is we can do some transformations. We can take the age and bucketize them. We can say, well, what if we wanted age to be categorical? It was continuous before, but what if we want to make a categorical version? Because we care about age ranges. So we say, okay, here are the boundaries, and we can basically have a bucketized column. And then we can also cross columns. So we can take two categorical columns and say, when we have education and occupation in specific pairings, to have TensorFlow find those rather than just having them in the jumble, in the haystack. We point out, here's a needle. Associate these two needles together, basically. And we can, in fact, even cross some of the things we transform. So here we have three columns crossed together. One of those columns is age buckets, which was itself, right, a bucketized continuous column. So you can begin to see there's a lot of options here. You can cross as many columns as you feel like having your computer work through, and then you pass in a bucket size, which should be the same order of magnitude as the sum of the orders of magnitude of the base categories. Ooh, run the cell. Okay. And so now that we've created our feature columns, sparse and dense, and then we have transformed them together. We're just going to group them. We're just going to make two arrays for all these columns that we created. So you see here we have our sparse columns, we have our transformed crossed columns below them, and then we have another variable for deep columns. And inside deep columns, we can do one further transformation. And here we take all of our previously categorical columns, right? Gender, race, native country, occupation. And what we have is we have this embedding column, right? Hopefully everyone remembers what an embedding is. And we remember that that was in the deep side of things, right? So we take these categorical values and we embed them into this 8-dimensional, in this case, space, so that they can be used by the deep neural network. We let the deep neural network eat up all the possible values so that it gets all the information. And so that's it, right? We create these two arrays, and we still haven't hooked up the data yet, of course. And so now let's create that, and it's going to give us some warnings about dividing by square roots. And so now we get to create our model. And what I have here is basically a simple helper function that generates a unique string to create a model directory to store all the values. And we have three different models here. We have both all the versions of our app. We have the linear regression, we have the deep network, and we have the wide and deep network. And so for the linear case, we've simply passed in the wide columns. Right? And then for the deep case, we pass in the deep columns. And then for the other one, we pass in both. And there's one more argument here, model directory. Model directory represents just the folder. It's literally a string. So we just pass in the folder that we want TensorFlow to use to store its kind of the artifacts of its training. And we'll see why that's useful in a moment. And so we have our model directory, our columns, and then for the deep case, we pass in hidden units. That's just a fancy word for the number of neurons we want per layer. So this is kind of part of this configuration. We can basically say, if I want a 2-layer network with 100 nodes in the first layer and 50 nodes in the second layer, we can just pass an array of 150. And if then we say, let's see what happens if we have 3 layers. You just say, comma, space, 25. And now we have a 3rd layer. And I can say, well, here's a 4th layer, and so on. And so with wide and deep, we combine all these arguments together. We have our wide and deep columns. And then again, we have our, let me scroll down for you. And then we have our hidden units as well. And so this is just kind of a helper function for me, right, to easily select which model to build. If you were just experimenting with this, you might, maybe you start with this, and then when you want to go to a different one, you could just literally just change the method call from DNN classifier to DNN linear combined classifier. And so that makes it easy kind of to play around. So let's go ahead and build this. And remember, we're doing deferred execution. So when I run this cell, it's going to return right away after printing some stuff about the configuration. But basically, it just builds the graph, but nothing is running through it because we haven't hooked up the data. So now we get to hook up the data, finally, the step that you've all been waiting for, maybe. And so what we have here is literally, oh yes, I should point this out. When we created our model, my get model function, we returned M and the model directory. M, of course, was our model itself, okay? And so, and externally, I'm also calling it M. And so we're going to pay attention to M. Every time I see M something, we know we're working with our model. And there's a number of method calls built into this class instance. And so we have m.fit. So this is the training. This will do all of your training looping. It will manage, saving off checkpoints and running, and it also supplies all the learning rates and things like that. So we do m.fit, and we pass in 2 things. One is the input function. That was the function from earlier that takes our data, given the file name, and pushes it into TensorFlow. So this function returns 1 training batch per call. So it returns the graph that returns 1 training batch. And then the steps, we say how many steps we want. If we don't provide this argument, it will run forever and you will be sad. So provide this value. So if we run this, again, something I probably should have run earlier, it will boot up TensorFlow, show me a number of warnings because we said info. And what's interesting about using info, once you get past the random warnings, which will go away, is that you get to watch the training happen in real time. Now remember, in our code, we didn't configure anything about learning rate. We didn't configure our choice of optimizer. We didn't configure what metrics for it to display, but it will basically supply some reasonable defaults already. And then, let's see here. So here we go. We have our initial set of kind of training loss, and so once it's set up, it runs pretty quick because this is not a huge model. And we have our training, all of our losses are printed by default. Of course, it doesn't have any notion of accuracy yet. And so we have, so that's it, right? We did it in 45 seconds. And our training loss, which is relatively meaningless to you, is just 0.27. But let's take a look at how it did in terms of accuracy, right? Because that's the piece we actually care about. And so for evaluation, it's just m.evaluate. So our operational model is we create our model, m, and we do m.fit, and we do m.evaluate. And with the evaluation, it's almost exactly the same arguments. This time I'm going to pass in the evaluation file, which I'm calling test file here, the value which was up here. You see here we have the test file. And let's see, and then it returns a results object, which contains a number of useful metrics, one of which happens to be accuracy, so I'm going to pull that out and display it. So we see here it does our 200 evaluation steps, and once I scroll past them all, which it shows, you can see here, we have this dictionary of values, inside of which we pull out just this accuracy at the bottom. So we did 83%. Sometimes this shows up as 82, sometimes it's 84. There's always a little natural variability. And one of the things that's fun to do, we don't have time today on stage to do this, but if you get this notebook, you can play around with it. You can change up the feature columns, which ones you use. You can change the transformations. You can change, of course, the model, how many layers, how big those layers are, how big the batches are. There's many, many, many different transformations that you can do. And what's neat about this kind of setup is that it allows you to easily iterate across different trials. You can play with different numbers and not have to muck up everything else. It's just like, oh, I want to change this thing. Okay, change it, rerun it. Change it, rerun it. And so you get a nice, tight development loop, which is really nice. And so the final thing that's useful, kind of, that we'll talk about today with this m dot something is m dot export saved model. Because when you're done training, when you finish optimizing all your things, you want to export a nice result. And so, let's see, the prediction side of things, right? And when we are doing prediction, we're going to want to have not the same training graph that we use for training. And this is because when you're training, we have lots of things built in for this back propagation and feedback loops and things like that and all the different metrics that you're measuring. But when we're running prediction, we're done with training, right? We don't want to change the values anymore. We don't really care how what gradients are coming out and things like that. We just want a blazing fast prediction graph that is nice and tight. And so we need to change the variables into constants. We want to strip out any nodes that are unnecessary, just make it blazing fast. And so TensorFlow has a built-in function to do that for you. So you can basically call export save model. This is another basically input function that helps map inputs to the graph that you basically don't have to touch, even if you supply new data sets. That's another cool thing about the way I've structured this for you. And then you basically just supply that function and a string path is the folder to save it to, and it just exports that model for you. So that runs pretty seamlessly. So it just loads up the graph and then exports it out for you. Keep in mind that this graph, once it's exported, is not something that you can use for more training, right? Because it's just the prediction graph. It's been stripped down. It no longer works for training. And so when you do want to train again, let's say you trained for 10,000 steps and now you have some new data and you don't want to start over. You want to start on step 10,001. What do? You can pass in the same model directory and it will use the checkpoint files that are already saved there, that it saved there for you without you having to do anything. It will just pick up where it left off. It will load up the existing variables, and it will continue training at step 10,001. And so that's a really nice kind of built-in feature of working at kind of this level of abstraction. So now that you have a prediction graph, you need to be able to do something useful with it, right? We want to answer those questions. And TensorFlow also has this thing called TensorFlow Serving, another open source package inside of TensorFlow that takes care of running your blazing fast model and at, basically in production on your data centers. And so it's a C++ binary that just works out of the box. You just need to load it up, configure it into whatever environment you may be running in, whatever. Maybe you have a containerized environment, maybe you have it running on some kind of hosted service, and it will just take care of that for you. And right now, Google has it's called Google Cloud ML Engine, machine learning engine, which it does training, but it also has a prediction service, which lets you load in those exported prediction graphs and basically spins up a scalable web server for you. And we hope, since we already released TensorFlow Serving as an open source thing, we want to see other options out there, right? So that's why the last bullet here, hosted across, I want to be able to add more bullets here so that you can have options, just like you have options to deploy your web servers to different places as well. And so, the ML engine, just as a brief kind of intro demo to that, you can basically, you create a model. There's this notion of models and versions. The model is just the shell for containing all the versions of your model. So you create a model, maybe you give it some name, and that's all you give. So again, you see that theme where we just provide a string and nothing else, and you're just supposed to know what to do with it. And so you give a string, and so you create a model, and that's kind of useless because you have no versions. So you create a version, and maybe you call it V1, and you pass in you need to pass in a folder, a path to, in this case, to cloud storage. So the export saves out, actually, let me just show you briefly here. I know we're kind of tight on time. So we saw here exported. It exported to this, let me scroll down for you. It exported to this folder, right? So we just did this. And so I'm going to go to that directory here and make this bigger first. And we're going to cd into this directory. And you see here we have two listings here. One is a .pb file, and then one is a variables folder. And so inside of that variables folder are just two small files that hold the saved variables. So the .pb is the structure of the graph, and then the variables are for the actual saved weights. So similarly, I have here, basically if you just upload these two files into the cloud, and then you pass in that path, and then you can create, and then you basically have a scale to zero, also auto scaling up web server that runs your prediction graph for you. So if you guys have ever used like App Engine, it's like a similar kind of experience there. And you can, of course, do all of this from the command line. You can create models and create versions directly from there. It's the same arguments. So you can script that out as you please. And then with prediction, you pass in the JSON. So basically then you've created a REST API, and you can use it. You can hit it from anywhere, mobile, embedded, whatever you want. It's just a REST API. So you pass in some REST call, and you can do this from the command line as well, and you can get back the responses as probabilities, as well as classes on the left, 0 and 1 being the predictions. And if you get it in JSON, it looks like this, as you would expect. And so they're telling me I'm running out of time. So basically, with TensorFlow, you can basically operate however you want. You can train locally and serve at scale. You can flip it around. You can say, I have a lot of data I want to train in the cloud, but for reasons of network latency, I want to be able to predict locally, right? So then you can operate this way because you have that common interface of using of these variables and save model.pb. By having these exported files, you can play between, you can put it wherever you want, and you can go back and forth as you please. And of course, you can do both in the cloud or both locally. That's the kind of the easy case. And so, again, my name is Yufeng. You can find me on Twitter at YufengG. And here are some resources. One is Machine Learning Engine, of course, TensorFlow.org. If you haven't been to it, it's a great site. Lots of good tutorials built into that. And then the bottom there, the two code short links. One is for what we saw today, census. And then the wide-indeed-code is a different repo I have, which basically is the same setup, but a different data set. a rather quite different data set. And this one is anonymized click data. So, working with anonymized data, it calls for some different approaches. There's a Jupyter notebook in there as well. So you can kind of see what was different and what was the same about using this model on a different data set. So then maybe you can take it and extend it to your data set, and then I'm hoping that this will help you accomplish that. And finally, I have TensorFlow stickers, if you guys are interested. Help yourselves. As you can see, I have a lot, and international travel is not getting any easier anytime soon. So save me some space in my suitcase, and thank you. Yeah.